great break. I'm a solutions architect with Rackspace, and I focus on AWS and AWS technologies. I work with Rackspace customers like yourself during migration to the AWS cloud, or help you refine your architecture that is already in the cloud. I've been doing this going on 6 or 7 years, starting at Amazon a few years ago as a solutions architect and as a developer, and now at Rackspace. I've worked with many customers, seen lots of AWS architectures, worked with lots of successful customers, worked with customers who might not have been quite as successful. But one thing that I've noticed and we've noticed are some key attributes about architectures in the cloud, specifically in the AWS cloud, and what those successful customers did. And that's what I'm here today to share with you and talk about, is some of the architectural best practices as you're moving to the cloud, the evolution that your architecture may go through, some of the best practices that I've seen, that we've seen at Rackspace, and share those with you today. My goal today is that when you leave here, that you go back to your teams or your company and you're able to share these with them and start the discussion. If you're interested in moving to the cloud, moving wholesale, bursting into the cloud, all of these are applicable. Hopefully you'll share those with your team. If you're already there, then these might be ideas for you to start thinking about, or to improve your existing infrastructure. So let's jump right into it. A quick question though, how many of you are actually already using AWS? Okay, good. So we've got some who are actively using it. And so that just kind of gives me a gauge for where to sort of target my talk. So one of the key attributes of an architecture in the cloud, and this isn't specific to AWS, but just in general, is that architecture needs to be scalable. In the cloud, we don't have access to physical systems. We have access to virtual servers, and we usually access those through an API or through a console, so we can't actually provision servers. I don't know about you, but I've been in companies where when I wanted to scale my system out, I actually had to start that process months in advance. I would have to determine what types of systems I needed, what their capacity was, go through the procurement process wherever I was, and perhaps go through several layers of approval, finally get the funding for it, get them shipped out, get them provisioned, and actually get them in service. So we would have to do that very well in advance. In the cloud, in the AWS cloud in general, we don't measure scalability in terms of weeks or even months. We actually start talking about scalability in terms of minutes. How quickly can we scale up our systems to meet current customer demand? And elasticity is one of the key attributes. We need to be able to very dynamically scale our architecture, our infrastructure, and our services and systems to meet current customer demand. We're no longer in a mode where we are predicting what it's going to look like at the end of the year during the Christmas rush or on Black Friday. We're actually building systems that scale dynamically to whatever our customer demand is. We provision when our customer needs it. And as part of this provisioning process, we want to make it as automated as possible so that our customer experience is the same whether a single customer is online or 1 million customers are online. Imagine a situation where you're needing to scale your system dynamically and it's based on some metric that you're using to determine when to add instances and when to remove instances. We don't want the customers to have to wait for you to provision an instance in order for them to use the system. So we want to make it as seamless and make the customer experience as transparent as possible. The other thing, the other part of scalability in the AWS cloud is frugality. Part of this dynamic provisioning is we start to look at things a little bit differently. We only pay for what we're actually using, and so we tend to use less. And because we use less, we pay less. And so our architectures on the cloud can be less expensive and easier to maintain. So a lot of times when I work with customers, this is where we start. This is a very, very simple architecture. I can't tell you how many small customers that I've worked with where this was really where they started. They had an engineer in an office somewhere, and their entire application was on a single box. They had the application, the web tier, all the business logic in the database on a single box. This is a lot of times where we start, and I just want to use it as a point of reference. How many of you have ever started here? Okay, good. It's common. I call this app on a box, and it's a very common starting point. So let's talk about some various techniques that we can use to move our app on a box into the AWS cloud and make it scalable. So talking about scalability just in general, and you see a nice graph on the left there that shows how we want our capacity of our application to match what our demand is. When talking about scalability, and some of these terms might be review, but they're very important terms. We can scale our application vertically, and by that I mean we actually take a single system. So imagine we have a very simple stack, which is a web server and an application server and a database. When we want to scale the web server vertically, we simply add more RAM, more memory to it so it can do more in-memory types of operations. We can add more processor power. Maybe we can add more virtual CPUs to it so that it can process more at a time, more in parallel, or more operations or operations quicker. Or we can scale vertically by adding more disk space. So we can do those types of things. Each one of those allows us to take on more capacity. So I call this, using a bigger box. And that only takes us so far, though. I can only scale vertically so far. I can only get a bigger box so many times before I have the biggest, the latest, and the greatest, and I can't do much more with it. So vertical scaling will take us the first step. That's our sort of first evolutionary process, is scaling our application out to handle load. The next step will be horizontal scaling. And horizontal scaling is simply taking an existing resource and cloning it and putting it into the pool and having it take on resources. So imagine, again, our web server. We're going to horizontally scale it. We've got increased load. Our customers are starting to use our system more and more. We simply add more resources to that pool to allow additional customers to be processed, additional requests to be processed. One of the side effects of this is we need the ability for this to happen automatically. And in order for it to happen automatically, our applications have to have a couple of properties that are very, very useful. One of those properties is statelessness. So in terms of stateless, that means we're not storing any information on the system at all. So we have a web server, for example, that's completely transparent. It just serves up web pages. It does some very simple operations. It doesn't keep any user state around. That's a good example, too, because it brings up the point. In a dynamically scaling environment, in an elastic environment where systems are being added and removed, imagine a scenario where you have a web server. It's a simple example, but it shows the point, where you have a web server that's actually serving up content for a user. That user logs in. You store session state for that web server locally on that system. In a dynamic environment, that system may go away at any point. So what happens to the user experience if you determine that you no longer need as many instances running as you currently have, and it takes that instance out of production? All of a sudden, that user state, that user session information is gone. And at that point, the user has to re-authenticate, potentially loses some valuable work. In a stateless system, we move that session state off to perhaps a cache, like a memcache server or something. We move it off so that whenever we scale the system down, the user can then just be sent through another web server. Another aspect of scalable applications is the fact that they need to be self-aware. And by self-aware, I mean when an application starts up in a very dynamic, elastic, scalable environment, they need to ask who they are, what their role is, what they do. And typically this happens in the form of, okay, I'm a web server. I have, this is the type of content that I'm serving. I dynamically discover my configuration in the cloud. In this case, we might go to S3 on AWS, the object store, and get configuration. It tells me what content I need to serve up, and I will then automatically attach myself to a load balancer. In the AWS case, that's an elastic load balancer. So these systems need to be able to self-start themselves, bootstrap themselves so that they can automatically come up and start taking traffic as soon as possible. So here's sort of what our application might look like. Our first evolution in the cloud, we bring it over to the cloud, we put a load balancer in front of it, we put multiple applications on it, we serve it from the database. This is not really specific to AWS, but just sort of demonstrates an example. In AWS terms, for those of you who don't use it, load balancers are termed elastic load balancers. Individual VMs, instances in this case, are EC2 instances, elastic cloud compute, and databases can be a different variety of forms. But we'll talk a little bit about some of these. The next thing we want to talk about in terms of scalability in the cloud, we can pretty effectively scale our applications. We know that we need to make them stateless, we need to make them self-aware. How do we deal with databases? In the database world, scaling can be accomplished in sort of a similar fashion, at least when we're talking about it vertically. When we scale vertically in the cloud on AWS, we do the same types of things. As our database starts running at capacity, starts showing perhaps performance issues, we can add additional CPUs so that it can process more in a shorter amount of time or simply process more. We can add RAM so that it can do more in-memory operations. We can add additional disk space so that we can accommodate a larger database. But as is the case with application scaling, vertical scaling with databases, again, will only take you so far. You can only scale so far. You can only get a bigger box so many times before you have to take some action and scale differently. This brings up horizontal scaling in the cloud, in particular on AWS. Horizontal scaling is a little bit different in that we can't just take a database and clone it like we would an application and have it start serving up traffic, especially when you're writing to a database. That's not very easy to do. We can, however, take specific use cases and scale them horizontally very easily. In the case of a database that has, for example, a very read-heavy workload, in Amazon you can provision what are called, when you're using Amazon's relational database service, RDS, you can provision read replicas. And essentially what that does is it spins up another database instance and asynchronously replicates data to that instance. Then your application can redirect read requests over to that read replica database. Now it introduces some it's an asynchronous process, so now all of a sudden you have to deal with data consistency issues. Is your application able to deal with data that is potentially a little bit stale? The process of migrating data over is an asynchronous process, so your application has to be aware. It has to be aware, number one, that data could be out of date, and that it needs to redirect read and write requests to the database to different locations. The other thing we can do in a read environment is caching. Now, caching is very useful in this case, as it allows us to actually take read requests and cache them for the application. Again, this removes some of the read pressure from both the primary database in this case and the read replica. We can actually place another layer above the read replicas and relieve more pressure off of the database. So in a read-heavy workload, it's very straightforward in AWS to actually alleviate some of that pressure, as long as you're okay with consistency. If you have tight consistency requirements and that data needs to be as up-to-date as possible, then you have to look at other options. In the case of a write-heavy workload, we have a different type of scaling that we can do. Again, we're talking about horizontal scaling. In a write-heavy workload scenario, you have a couple of ways of approaching this. As your database starts to grow, your business starts to grow as well, and your database is starting to feel the effects of that. We need to be able to alleviate some of that write pressure on the database. And in the case of a write-heavy workload, we can shard the database, or we can partition it. Both are types of partitioning, but when we're talking about sharding, we're talking about taking your database and partitioning it up in some logical fashion. In this case here, I have a simple application maybe that has it has users, it has products, and it has orders. And in this case, I've decided to partition my database along user lines. So users A through H are on one database, I through S are on another database, and so on. Now this, if you have a database where write requests are distributed fairly uniformly across all of these users or whatever your tables are, this works out fine. Now all of a sudden you've reduced the pressure on your primary database, in this case by a third or by 2/3. And this can work very well for you. It also requires, though, application knowledge of this change. So you can't simply go in and shard your database and your application be completely unaware of it. There has to be some translation layer that says, okay, for users X, Y, and Z, we go to this database. For users 1, 2, and 3, we go to another one. Whether that's by hashing, whatever technique you have, there has to be some knowledge in your application to direct yourself to the right database. The second way, most common way we see AWS architects or architectures deal with scaling a write-heavy workload is through just simple partitioning. So in this case, it's very similar to sharding. We actually partition the database up. In this case, instead of partitioning by user, we're actually taking functional sections of the database and putting them off into their own database. So we might put users in a database, products in another, orders in another database. This is very similar. You can reduce your write contention on your database, but again, your application needs to be aware of that, and this assumes perhaps that you have the same type of workload on all of your databases, but it is an effective way of partitioning your database and scaling it out horizontally. And you can use a combination of caching and read replicas for write-heavy work or for read-heavy workloads and write-heavy workloads in the same database. It introduces the complexity of your database, but in an environment where you've reached the vertical scalability limits of your database, you need to do something to alleviate that pressure on it. And there are actually third-party softwares out there that will help you do this. So that kind of covers the first part or one of the key attributes of architectures in the cloud, and specifically on AWS, the scalability of applications and databases. Scalability is one of the key attributes. You have to be able to do that. The next topic I'd like to talk about is another key attribute, and that's resilience. The cloud, we'll talk a little bit more about this later on in the slide deck, but the cloud is changing constantly, and the environment that you're working in changes constantly as well. And by resilience in this case, I mean your application needs to be able to run in the event of an outage. It needs to be able to run when things fail, and it needs to be able to run and recover automatically. What does it mean to be available in the cloud? Well, it means a couple of things. Resiliency is the first thing, and like I mentioned, it's that ability of your application to recover from and respond to outages or failures of just about any kind. It means that your application is fungible. And by that, I mean individual components in your architecture need to be replaceable. They can't be special. They can't be one-off components that can't be replaced at any point in time. You need to be able to swap them out. You need to be able to scale them out. They also your application needs to be fairly graceful. And by that, I mean when failures occur, you need to expect them and actually behave differently when things happen. For example, if your database fails, what are you going to do? Instead of simply failing and the user getting a 500 error when they go to your website, for example, you need to provide a mechanism that provides for a better user experience. Maybe you degrade to read-only mode. What happens if one of you're running an e-commerce site and part of what you do is provide recommendations to your users? What happens if your recommendation engine fails? What are you going to do? You're not going to fail your website, but you're going to recover from that, and you're going to do it gracefully. That's the point here. So how do we do that? How do we actually architect our application for availability in the cloud? So there are a couple of things that I'd like to talk about here, and not all of these apply to every application, but these are fairly common techniques and best practices that we've seen across cloud-based architectures that allow them to be highly available. The first one, and some of these can be standard software engineering practices that maybe some of you have seen. The first one is decoupling services, and I'll talk about a couple of them at the same time. Decoupling services and asynchronous operations. So imagine our monolithic application that we have. It has functionality, or it has several different areas of functionality. Perhaps we want to break out some of that functionality and provide them in different services. We want to decouple them and make them less dependent. So now our main service actually calls out to a secondary service to make a request. And so we decouple it in that way. That's very useful for a couple of reasons. Number one, it allows the two services to vary independent of one another. They can now actually scale independent of one another. So when the primary service scales, that doesn't necessarily mean that we also have to scale the secondary service. The secondary service can scale as it would like. It also means and opens the door for us in this case to introduce asynchronous operations. And we'll sort of tie all of this together in just a few minutes. But asynchronous operations allows us to, say, for example, place a queue and start processing requests a little bit differently. So imagine an upstream service that's servicing customer requests. It needs to call out to the downstream service. Instead of making a synchronous call directly to that service, now it places a request, it serializes it and places it into a queue. And then the downstream service polls that queue, takes the job out of the queue, processes it. Perhaps both of them monitor and change a status database somewhere so that they can tell what's going on. But this is very important because it allows applications and services in the cloud to fail and scale independent of one another. So here's a great example. Again, a website, you're queuing up requests for, say for example, it's image processing. We want some operation to be done on an image. And so instead of actually synchronously making that request and waiting for a response to come back, we place the request in the queue. Later on, the downstream service processes that request. If we suddenly have a spike in traffic and the downstream service can no longer keep up with the number of jobs that are in the queue, it can simply continue processing and in the meantime start to scale out and bring up another instance online to start processing these. The upstream service is completely unaware of this. It continues to queue up jobs. The downstream services start to spin up more EC2 instances in the cloud. They start burning their way through the queue, and pretty soon the queue is back down to normal, and the downstream service scales back down. So these two services now scale independent of one another. The upstream service is completely the upstream service is unaware that it had overwhelmed the downstream service, and it's completely isolated. So it allows us to build a highly available application that can scale independently and transparently to the upstream user. One of the other things that we want to do in our highly available architecture is identify single points of failure. And there are obvious places where these occur. Thinking about our simple software stack that we showed where we have a web server, maybe an app server, and a database, obviously each one of those is a single point of failure. If, for example, the web server goes down, that means the entire system fails. If the app server goes down and the web server can't call out to it, then that means that the entire stack goes down. The same is true for the database. So we want to identify those and come up with strategies and plans for mitigating the failure of any one of those single components. In the case of AWS, we look at applications and services like Elastic Load Balancer. We look at Route 53. We look at S3. We look at all of the other services like the relational database service to help us identify those single points of failure and come up with plans for mitigating a failure there. So the next item on the list here, I don't know how many of you ever worn a pager and been woken up at 2 o'clock or 3 o'clock in the morning. Usually it's Sunday morning. It's been a long night already. Metrics and monitoring are one of the key attributes of a highly available and scalable application in the cloud, and I'll tell you why. Think about again, a customer-based application where we measure our customers' satisfaction with our system based on, for example, latency. So we measure how long it takes a customer request to be satisfied, and it doesn't have to be an actual end user, a person. We could actually have a service that's simply an API, and our customer is another service somewhere upstream that's calling us. We use that metric in a variety of different ways, and the two most common are these. Number one, we use that type of metric to trigger scaling in our system. So for example, our website, it's handling customer requests, and we monitor latency to determine how effective that website is doing. We use metrics, and in AWS, we have services like CloudWatch and custom metrics that allow you to monitor these. We can use those metrics to trigger scaling events. And scaling events are used by auto-scaling groups in AWS to automatically grow and shrink your application pool. So we can define a metric, say latency, customer latency, and use that and set a baseline, a low watermark for it, and say, okay, 10 milliseconds is our baseline level of latency that we will accept. If latency ever exceeds 10 milliseconds or maybe somewhere before, we want to start adding instances to our application pool. If latency drops below that, then we can start taking instances away from our pool. So that allows us to scale our application very easily and very freely. It allows us also then to provide additional input into our DevOps team. So for example, we also set up another alarm on a metric in AWS that says if it ever exceeds 15 milliseconds, go ahead and trigger an alarm and notify our DevOps team and or whoever's wearing the pager that night, and let them know. And this also sort of paves the way for us to provide additional layers of metrics and monitoring. So now we have a highly available and scalable application with multiple layers of service. We can expose these metrics and provide them to our operations team when they need them. So continuing down this path of highly available systems and architectures in the cloud, one of the things that you may have talked about outside of here are microservices. So microservices or microservice architectures or service-oriented architectures, it depends on who you talk to and how they call it, but this is really a logical extension of decoupling and making our operations asynchronous. In a microservice environment, architects will actually take their services and completely decompose them. So for example, on a previous slide, we talked about databases and services that covered users and products and maybe user orders. We might actually break those out from a single monolithic application and a single monolithic database into 3 separate services, a primary service and then sub-services that are called out, and completely separate databases. This allows, again, for each one of those services to scale completely dynamically from the other one. So say for example, now we have a user service that is called and used for any actions that revolve around our customers or users, and we have one for our products as well. Now that particular service can scale completely independent of the other services. We can make it highly available. We can make it super scalable depending on what the needs are. And we can do the same thing for all of the other services. It's a very cool way of decoupling all the components in your system and making them very independent of one another. And also from a developer's perspective, when we move to a microservices approach, it allows development teams to vary independent of other development teams within an organization. At Amazon, the Amazon.com retail site, the architecture that you see there is very much a microservice or service-oriented architecture. And as a developer at Amazon, I worked in teams that used different development methodologies. Some were agile, some used pair programming, some used Java, some used C++, whatever you did. Breaking your application down into smaller services as it grows allows you to vary many things. Now, what was kind of interesting is as I was preparing for this talk and actually thinking about microservice, the tweet that's on the screen there actually showed up in my Twitter feed on one of the days I was working on it, and it's very appropriate because what it really does is, so now, it's 2 o'clock in the morning, your pager goes off, you've got a monolith for an application, you know where to go looking for the smoking gun. At 2 o'clock in the morning now, it is really true. Now you have an outage, it's like a murder mystery. You've got to chase down this problem across potentially tens or hundreds of microservices. So you have to use this with caution, and it's easy to over-engineer it. Pets versus cattle. This is another term that we use in the cloud, and many of you may be familiar with it. I actually stole this slide this was given by a guy at CERN some time ago. And I'll start by an example. About 10 years ago, I worked for a small startup, a small security startup near Portland, Oregon, and we had a small office space, and in that office space we had our own small data center. And like data centers, it had all the common components. We had racks, and we had servers, and we had monitors, cabling, the whole 9 yards. And we also had names for each one of our servers. So when you walked back in there, you saw a name taped to the front of each one of the servers. And if one of those servers went down, we talked about it by name. If there was a problem with it, we nurtured it back to health. As it was having a power supply replaced, we were there with the tech, watching it, making sure it was doing okay, and then we brought it back into service, watched it, made sure everything was going fine, and moved away. We loved our servers. That's exactly the pets use case here. We name things, we nurture it, we love it, and that's okay in an environment where you actually have physical systems available to you. In the cloud, it's a little bit different, though, and thus the pets versus cattle. In the cloud, in the majority of cases, when one of our servers gets sick, we don't treat it the same. We treat them more like cattle, where cattle are generally the same, and when one cow goes bad, you go get another. You take it behind the woodshed, do whatever you need to do, and come out with a new one. So that's really, and in the case when you think about building a super scalable, highly available application, that's really the approach that you have. You don't have time or resources available to go chase down all of these problems. It's much easier just to get rid of that server, bring up another one in its place. And actually that's a very common practice, especially in a cloud architecture where you are in a shared environment. One of the things that we recommend doing is monitoring performance of individual instances and establishing a baseline. If your EC2 instances in the cloud ever start exhibiting problems, performing poorly, just go ahead and pull the plug on it, terminate it, and bring another one up in its instance. We no longer nurture things back to health. Now, there are special cases, though, where we do need to do this. There are special cases where we have commercial off-the-shelf applications that really aren't built or architected for the cloud, so they really can't be made highly available. You can only really have one of them up and running at one time. It's a third-party piece of software, so you don't have access to the code, and so you can't make changes to it. And so there are cases where we still do need to treat individual systems like pets. We need to care for it and nurture it and provide mechanisms for it to recover should we have problems with it. So one last slide, or I should say 2 more slides on high availability in the cloud before I finish up this section. I won't spend a whole lot of time on databases and high availability in the cloud. High availability in the cloud for databases is very similar to high availability in an on-prem solution. You have to replicate in one form or another. In Amazon on AWS, their relational database service, they provide a managed service that allows you to replicate your databases, whether it's Postgres or MySQL or SQL Server or Oracle or MariaDB or their new Aurora database. They provide a managed service that allows you to gracefully fail over from a primary to a secondary server. Now, you can still add caching to this so that when that failover does occur, because there is a finite amount of time when databases are failing over where there could be some availability issues, you can put caching in front of that and gracefully fail over to a read-only state to make the end user experience a little nicer. Actually, there's one more slide. I don't know, how many of you know Werner Vogels, CTO of Amazon AWS? So one of his quotes is at the bottom there, and it's very true and very telling. Everything fails all of the time. And when we're thinking about availability on Amazon, on AWS, we need to keep this in mind. At some point, everything you're using on AWS will fail, whether it's your application, whether it's the instance itself, whether it's the piece of hardware that virtual device is actually running on, a switch in one of their racks, an availability zone, a database, everything will fail at some point. And as developers or architects of highly available and scalable solutions, we need to be prepared for that. We need to put in place mechanisms that allow us to gracefully fail over. We need to know what we're going to do if the database fails. We know what we're going to do if in Amazon terms of an availability zone, one of their data centers fails. How do we recover from that, and what types of resources can we use to solve that? Everything fails all the time, and the quote up above is it's really up to us. Amazon can provide us with all of the resources and services, but we need to use them to our advantage. So up to this point, we've talked a little bit about scalability and availability in the cloud, and I've shown you several different common best-known methods as best practices for addressing those types of things in the cloud to make sure that you're evolving your application in the right direction. One final point, and I'm not going to go into it in any detail, but I wanted to talk just a little bit about how applications are secure in the cloud. And it's very common to talk to customers who are interested in moving their HIPAA compliant, high-tech compliant, PCI compliant workloads to the cloud, and specifically to AWS. And I'm not going to go into any detail here other than to say all the pieces that you need to do that are available on AWS. AWS has a BAA now, which they just brought on, I think, a year or two ago. So you can now run HIPAA and PCI, HIPAA compliant workloads with the BAA. All of the bits and pieces are there for you to do that. It's just a matter of architecting your solution and finding what services and features are available on AWS for you to use. And which is kind of a nice segue into really why I'm here today. I'm part of Rackspace's new fanatical AWS support team, and this is really what I do. I spend all day talking to customers, working with customers, helping them work through their architecture and any issues that they have. I know all of the AWS, most of them, the AWS services and features that are out there, and so I can help you walk through that process and pick out what's best for you. That's really what my job is, and what I love doing is working with customers. Finally, I want to leave you with this one last word. So regardless of how scalable your application is, how available it is, how secure it is, one of the key point, the key takeaway here is that your application needs to be adaptable. You need to be able to adapt to the changing environment at AWS, the changing infrastructure there. You need to be able to adapt to your changing customer requirements, and you need to be able to adapt to your internal engineering resources that you have available to you. This is the key component for all of these architectures, sort of the underlying attribute of all of them that has made them successful. That's all I have. Thank you all very much for coming. I appreciate you coming and sitting through my talk, and glad to have you all here. If you have any questions, want to talk to me about AWS or architecture or architecting for high availability on AWS, I'll be here for the rest of the day. Catch me out in the hall or talk to me whenever you want. Thank you.
Next up here in the main room, we will have Rackspace Distinguished Architect Adrian